We're taking a look at worksheet number 8. 4 questions on this worksheet, 4, 7, 8, and 12, starting with question number 4. Question number 4 says, calculate the distance from a 3 coulomb electric charge with the electric field strength is 1.09 times 10 to the 11 newtons per coulomb. Let's draw this out. Sometimes it's helpful to draw it out to determine whether you have a producer, experiencer, uniform, non-uniform. This is my 3 coulomb charge. I want to find the field strength right here, a certain distance away from that 3 coulomb charge. That, I know that electric field, right? It's 1.09 times 10 to the 11 newtons per coulomb. Does that 3 coulomb charge produce or does it experience that field of 1.09 times 10 to the 11? Is it causing it or feeling it? It's producing it, yeah. Like, think of it this way. This charge of 3 coulombs, this charge cannot experience something over here. We've got a field strength a certain distance away of 1.09. This guy can't be experiencing something if it's not at that location. Does that make sense? If you've got, or if you're looking for a field strength a certain distance away from a charge, that charge has got to be causing the field. You cannot experience something that's over there. That 3 coulomb charge can't experience a field over there. The only thing it could have done is produced that field. So we're going to use one of our producer equations. Is it uniform or non-uniform? Well, what's the field look like surrounding a positive producer like this? That would be a non-uniform field, right? So we're going to use that first equation, that non-uniform producer equation, E is equal to KQ over R squared. We're going to rearrange this to solve for R. Take the R squared up by multiplying. E times R squared is equal to KQ. Let's rearrange that. Take the E down by dividing. R squared is equal to KQ over E. And then finally, we solve for R. What are we going to do? Square root it. Good. So it becomes the square root of KQ over E. Now, I think the math on this is pretty straightforward, relatively speaking. We stub our numbers in there. Don't forget to square root. And we get a value for R there of 0.497 meters. Look, you've got the field strength 0.497 meters away from this charge. This charge can't experience that field strength 0.497 meters away from it. Okay, it's got to be producing that field. It's like me saying, hey, what's gravity 100 kilometers above the surface of the Earth? Well, the Earth isn't experiencing that gravity 100 kilometers away from the Earth. It must be causing the gravity 100 kilometers away from the Earth. Okay? Now, if I had a spacecraft or an airplane of some type that's 100 kilometers above the surface, okay, of the Earth, that could be experiencing it because it's at that location. But you can't experience something if you're not at that location, if you're a certain distance away from it. All right, I want to look at number 7 as well. What's the magnitude of the net force experienced by an electron if the electric field experienced is 1 times 10 to the 3 newtons per coulomb? We don't know whether this is uniform or non-uniform. There's no indication whether it's a uniform or non-uniform electric field. But we do know that this electron is producing or experiencing this field. It's the word, right? When you see the word experiencing, then it's going to be an experiencer. So we're going to look at that middle equation. E is equal to F over Q. And we're going to rearrange this to solve for F to get Q times E. We sub in our numbers there. That's pretty straightforward. By the way, not the sign of the charge. Just like every other equation, we drop the sign of the charge. We end up getting a magnitude of the force here of 1.60 times 10 to the negative 16 newtons. Now, we're not asked to go to the next step, but if we were asked to solve for the acceleration of this electron, how would we go about doing that? Yeah. Good. Divide by the mass. The force needs to be with you, right? Once the force is with you, then you got to use the force. And you do that by dividing by mass. Okay, next question that I want to go over is number 8. Two charges in a straight row. The first charge is a value of this, positive. Second one is negative. And we want to find, and it's 4.5 centimeters to the right of the first one. What's the direction and the magnitude of the field strength midway between those two charges? Let's draw it out here. First charge, 5.00 times 10 to the negative 5 coulombs. Second charge is negative 2.50 times 10 to the negative 5 coulombs. Okay, my distance here is 0.0450 meters. And we want to find the field strength right here, midway between, halfway between those two charges. To do this, you can remember from the podcast that you guys watched on Friday, you're going to find the direction of the field caused by both of them at that point. Let's look at one at a time, just like we did with forces. One at a time. Charge 1 is positive. So forget about charge 2 here for a second. 2 doesn't exist in your mind right now. Just charge 1. The field caused by a positive producer points which way? Inward or outward? Outward. Field always points away from positive. Look, the field points away from the positive. Look, it points this way and this way as well, away from the positive. But what are the 3 words that I say with this one and this one? I don't really care. I guess that was 4 words. I don't care. That's 3 words. I don't care about those guys because I'm not trying to find the field there. I'm trying to find the field over here to the right. It points away from the positive producer. Now let's pretend 1 doesn't exist. Pretend 1's not there. 2 is a negative producer. Which way does the field point surrounding a negative producer? Towards or away? Towards it. So we're going to say that the field caused by number 2 is toward the negative. Now, there's also this one and this one, right? But we don't really care about those because we're trying to find the field strength midway between. So we care about this one. Blue is away from the positive producer. Green is toward the negative producer. Is that clear, guys? Is that clear? Being able to draw that diagram is critical for one of your questions on Monday's test. Okay, you will get a question where you need to find the net electric field strength, and to do that, you need to be able to draw that diagram. Okay, understand why it's to the right, why they're both to the right, and when one of them would be to the left, or up, or down, or whatever the case may be. Okay, we calculated each of these fields now. We say KQ1 over R squared, 8.99 times 10 to the 9, times Q1, which is 5 times 10 to the minus 5, divided by R. What's the value of R? 0.450? Half of that. It's half of that. We want to find the field strength halfway between. So the distance from the blue positive producer number 1 is 0.0225 meters. And of course, as Venture said a second ago, we've got to square that. I get 8.879 times 10 to the 8 newtons per coulomb. Now, E2, found in the same way, numbers are just a little bit different here. That gives me a value of 4.44 times 10 to the 8 newtons per coulomb. Now, how do we combine these? How do you find the net field there midway between those two charges? Yeah, add them up. We're going to say 8.879 times 10 to the 8 plus 4.44 times 10 to the 8. What did we need to watch out for, but didn't really come into play here? The negatives, right? Why are they both positive here? Yeah. Like fundamentally, yeah, but like In practice, we made them both positive because they're both pointing in the same direction, both pointing to the right. It's because of the negative and the positive producer, yeah. Okay, but in the end, what we really care about at this point is which way is the field? They're both pointing to the right, so they're both positive. One was left, we make it negative. We add those up, by the way, we end up getting 1.33 times sort of the 9 newtons per coulomb. It's a positive value, so that means the answer's to the right. Yep?
Why did you half the R?
Why did I half the R? Can anybody explain that? Why did I half the R? Matthew?
You're figuring out the force in the middle.
The field strength, not the force. Yeah, you're trying to find the field strength in the middle, halfway between them. The distance between 1 and 2 is 4.5 centimeters. So the distance from one of them to the middle is half of that, 2.25 centimeters. Now, Matthew, I think you just, I think you were thinking the right thing. You just kind of said it wrong a little bit. You said you want to find the force in the middle. Careful there. The only way you can have a force is if you have a producer and an experiencer. What is experiencing the field in the middle there? Nothing. Not as far as we know, anyways. Nothing's given to us. So as far as we know, there is no force in the middle. That's okay. We're only trying to find the field strength in the middle, not some mysterious, perhaps non-existent force. Okay. Okay, the last one that I want to go over is number 12. And so it says, an electron sits between two charged parallel metal plates 10 centimeters apart. Here's the electric field between them. What's the potential difference? What's the electric force? What's the acceleration? We don't know which plate is supposed to be which. We're not told that, but I'll draw it like this. The electric field points away from positive. It points toward the negative. Tell me, before we go on to solve this question, tell me, if the electric field strength between the plates is 2.5, what is the electric field strength right here? 2.5. What is it right here? 2.5. What is it right here? 2.5. Good. What is it right here? 2.5. It's a uniform electric field between two plates, which means that the field strength is going to be the same no matter where you are between the plates. Make sense? As compared to this situation, where the field strength here is one value and the field strength here is a different value, right? If you had to plot a graph of the electric field versus distance from the producer, what would this graph look like at the top? Yeah. Good. I like the sound effects there too. I won't try to repeat it. It curves downward, right? That's an inverse square relationship. E is related to 1 over r squared. What about this graph? E versus r being the distance, let's say, from the top plate. This distance right here from the top plate. What would that one look like? Here's a good one. Okay, Bree? It would be a straight line, horizontal like this. Does that make sense? The field strength is the same. If you're 1 centimeter away, if you're 10 centimeters away, the field strength is the same value. Okay? All right, let's go on and solve this question now. What's the potential difference across the plates? This is a uniform field. We can take a look at our last two equations, specifically the producer equation. By the way, whoops, should not have a vector sign over that. By the way, delta V is potential difference. We talked about this a little bit earlier on in the unit. We talked about this in the podcast on Friday as well. It's not energy, but it's close. It's energy per coulomb. It's the energy per coulomb. It's like saying, for ease of math here, let's say we have 25 of us in this room. Let's say the total amount of money we have in this room between all of us is $100. That's energy. Money is energy, $100. How much money per person do we have? on average if we have $100 total? 4. That would be electric potential. Okay, does that make sense? So the energy is is $100. The potential is $4. So they're related to each other, potential difference, energy, but they're not the same thing. Energy is total, potential is energy per coulomb or money per person. Okay, that's what we're looking for. E, 2.5 times 10 to the 3. D is 0.10, which gives us 2.5 times 10 to the 2. And what are the units for that? (2.5 times 10 to the 2 volts. Okay, 2.5 times 10 to the 2 volts. What's the magnitude of the electric force? This is a uniform field. Take a look at the other equation that we haven't used for a uniform field. E is equal to F over Q. Let's solve for F. We sub our numbers in there, and we end up getting for that one 4.00 times 10 to the negative 16 newtons. Doesn't give us a direction, right? But that's okay. We're asked for only the magnitude. Finally, what's the acceleration experienced by the electron? How do you find acceleration? Force needs to be with you. Is the force with us? Okay, let's use our little Jedi training here now. How do we use the force? Yeah, A is equal to F over M. We take that value, divide it by the mass of the electron, and it gives us 4.39 times 10 to the 14. Hey, here's a kind of an understanding question for you. That's a small force, right? It seems like a small force, 10 to the negative 16 newtons. How can we have such a big acceleration, 10 to the 14 meters per second squared, with such a tiny, tiny little force? Mass is so small, right? It doesn't take much to accelerate a tiny little thing like an electron. Okay, we got a force that's not very big. We have an electron whose mass is even smaller. So that gives me still a pretty big acceleration.